Welcome to Khetz tutorials, and in this video I'll be doing hyperbolas, and this is the second video under this functions section, right? So this is also under revision in a way, but you just have to know it to solve problems which are going to come under this section. So this section I'm going to talk about hyperbolas. Right, so let's start. You are probably familiar with hyperbolas written in the general form of y is equals to a divided by x minus p and then plus q. So now we're just basically gonna break all of this down to explain all of these variables and what they do and what we know about hyperbolas. So the first thing that we know about hyperbolas is that they have two asymptotes. And basically, just a revision about the definition of the asymptote. So your function or your graph will approach this asymptote, which is basically a line, either a vertical or a horizontal line. It will basically, so the graph approaches but never touches. So now we said hyperbolas have two asymptotes, and these are basically the ones which I drew, and I'm going to use these to explain quite a few things. So let's start by talking about some of the properties of hyperbolas. So let's start somewhere here and say if a, so from the formula which you have, I have a formula which I just wrote here, is the general formula of your hyperbola, and we're saying that if a is greater than 0, now we expect our hyperbola to be situated in the first. So let me just draw it properly so that you see that it approaches. So this is the asymptote known to us as x equals to p. So now we already know the function, or we already know the role of this bottom part of the equation. It gives us the vertical asymptote. So x subtract p equals 0. So x equals p is our vertical asymptote. And then also we have y equals q. So y equals q will give us our horizontal asymptote. We now have the roles of both p and q, and now as I was about to start, basically I just about to explain the role of a. So you can see that the only thing that's left to explain is a, because we know that p gives us the vertical asymptote and q gives us the horizontal asymptote. So just to draw this, so you see that the graph actually approaches but never touches either of these lines because they are asymptotes. For a greater than 0, you have your graph occurring in the first and the third quadrant. So it will look something like that. You probably do a much better job of drawing it, but I hope you get the point, that it will actually occur in the first and third quadrants of your plane, your Cartesian plane, or whatever the case may be. But more specifically, it will occur in the first and third quadrants of its asymptote. So you can find that you actually have, so please note that these lines currently are just the asymptotes and not your x and y axes. So you can actually find that your x and y axes are somewhere here. So you can basically find something like this, which is, so let's say this is the x and this is the y. These two lines are not our axes. They are basically the asymptotes, which can be situated anywhere around the Cartesian plane. So the graph occurs in the first and the third quadrant of its asymptotes. So let's just make a note over here. So a hyperbola with a greater than 0 occurs in the first and third quadrant of its, and this is the key term over here, of its asymptotes. So your role is therefore not to put your hyperbolas with respect to the axes, but with respect to their asymptotes. So the first thing would be to find the asymptotes and then sketch your hyperbola according to those. So now that is the explanation of your A, P, and Q. And I only defined or only described when what happens when your A is positive or when A is greater than 0. So now let's talk about when A is less than 0. So when A is less than 0, you basically have your hyperbola. So your hyperbola, as you saw, consists of two sections. And one of the sections when A is less than 0 will occur in the second quadrant, and the other one will occur in the fourth quadrant. Right? So that is for the case where your A is less than 0. And just as in the previous case, y equals to q is one of the asymptotes, and x equals to p is another asymptote. So now let's move on to the axis of symmetry, which basically describe how you can actually find the half point of this division which the asymptotes made. So even though we know that the asymptotes actually divide these into quadrants, you also have another line of interest, which is quite interesting. So you basically have two lines actually, which look something like that. And they describe how you can further put segments or how you can further divide the quadrants. So as you can see, there's a division, there's something, the space here, the space there, the space there, and space there. And these lines actually define the axis of symmetry. So axis of symmetry, axis of symmetry. Let's just write AOS. And you can actually find the equations of these axes of symmetry. So let's take this to be y1, the positive one. So there's a positive one, it's going up in that direction, it's positive. And you have the negative one, it's going in that direction over there. So let's denote each of these as y1 and y2. So y2 is this one, which is negative, and y1 is a positive one. So now we can describe these using whatever we have in the formula. So to find the formula of y1, basically say x, subtract p plus q, and to find the formula of the negative axis of symmetry, you say y2 is equals to negative x plus p plus q. And both of these will give you the equations of the axis of symmetry. So if a question comes and it says find the axis of symmetry of the following hyperbola, you just have to come to your equation up here and just basically take the values of p and q and come down here and take this formula to form your equations for the axis of symmetry. You're basically going to say, for the positive axis of symmetry, you're going to say y1 is equals to x, subtract p plus q, and for the negative one, you're going to say negative x plus p plus q. That is basically how you do that. And sometimes, or basically all the time, you may be asked to find the point of intersection. So as you can see, these axes of symmetry actually intersect the graph at some point. So the axis of symmetry also applies when, just so you know, it also applies when a is greater than 0. I'm just using the graph where a is less than 0 to explain this. So the green section which I have here, or the green cross which I have here, indicates the point where the axis of symmetry actually cuts the graph, and the blue cross as well indicates the other point where the axis of symmetry cuts our graph over here. So to find the point where the axis of symmetry actually cuts, there are two cases. So let me just write here and say point where axis of symmetry cuts our graph. There are two cases. We have a case where a is greater than 0 and a case where a is less than 0. So as you can see, only one of the axes of symmetry when a is less than 0 actually cuts here. And if I were to draw similar lines for axes of symmetry here where I have a positive graph, I'd say that only one line, which is the positive one, cuts the graph, right? Cuts the graph, only one of them, and the other one actually doesn't. So the same thing applies to both sides. Only one of the axes of symmetry will actually cut the graph, and that is why we have to treat these differently. So for the case where we have a greater than 0, the coordinate, you can find the actual coordinate where the graph actually cuts the axis of symmetry, and that is found by square root of a plus p. So now please note that when finding the point of intersection of the axis of symmetry to the graph, you actually ignore the sign of a, because you can't actually, with the level of mathematics which you do right now, you can't actually find the square root of a negative number. You don't do complex numbers in grade 12. So you basically want a real solution or an actual answer after doing this. So just make sure you convert your a into a positive when substituting only into the point where your axis of symmetry cuts the graph. So to find one of the points of intersection when a is greater than 0, as you saw, that it actually cuts 2 points. So one of the points is given by square root of a plus p, and the y of that is given by square root of a plus q. And the other point where it cuts when we have a greater than 0 is the point negative square root of a. So the negatives on the outside, please note, plus p, and you also have negative square root of a plus q. So basically just change the sign of the answer which you get after computing the square root of a. So now when you have a less than 0, the 2 points where the axis of symmetry intersects the graph are negative square root of a plus p, and the x coordinate would be square root of a plus q. And here you'd have the other point would be square root of a plus p. The other point would be square root of, so negative square root of a plus q. So these are the points where the axis of symmetry cuts each of the graphs, or any type of graph, depending on whether the graph is positive or negative. So a greater than 0 or a less than 0. So just as we discussed the domain and range for parabolas, we're going to discuss the domain and range for hyperbolas. So let's come up just so we see and we can actually try to make sense of this, or make sense of what I'm about to write. So let's start with the domain. And once again, the domain is the description of all the x values which are covered by the graph. So for the domain of your hyperbola basically have x occurs everywhere, because as you can see, it goes on infinitely into the negative side and infinitely into the positive side, but there is a value which it doesn't touch, or there's a value which it doesn't include in its definition, and that value is p, which is the asymptote. So x covers all of the values in the Cartesian plane except p, which is the asymptote. This can also be denoted as x, and you have your round bracket from negative infinity to positive infinity, and x not equals to p. So these are the two ways which you can actually describe your domain. And moving on to the range, the same thing basically applies, but we're now dealing with the y values. So as you can see, the graph actually occurs, it can go all the way up to all the values in the y direction upwards, and it can go all the way up to negative infinity, all the way to positive infinity, all the way to negative infinity. But there is a, if you check the blue line, there is a value of y which it doesn't touch or it doesn't include in its definition, and that value of y has to be excluded. Excuse me. That value of y has to be excluded because it is an asymptote, and we know that an asymptote, it actually approaches but it doesn't touch the value. So the values of y for a hyperbola are actually all the values in the Cartesian plane or on the y-axis except the value of its asymptote, which can also be denoted or written as all the values from negative infinity to positive infinity, and you actually have to explicitly exclude your asymptote. So that is basically all I had to discuss with regards to hyperbolas. And in the next video, I'm going to be talking about yet another form of function which we actually have to know about. And I hope you got everything in this video which you wanted to know about hyperbolas. If anything was unclear, just feel free to comment in the comment section. If you like this video, just give it a thumbs up. And if you haven't subscribed, please subscribe to my channel. That will help a lot. I'll see you guys in the next video.